Thermodynamics is the study of energy, heat, and work. It explains how energy moves between objects and how it changes from one form to another. To understand thermodynamics properly, we first need to learn some important basic terms such as system, surroundings, state functions, and the difference between extensive and intensive properties. Let's go through them one by one. Let's understand what is a system and surroundings. In thermodynamics, a system is the part which we are studying, or simply we can say that which is under our observation, and everything outside it is called the surroundings. For example, if we take a cup of hot coffee, the coffee inside the cup is the system, and everything around it, including the air, is the surroundings. Now, based on how a system exchanges energy and matter with its surroundings, we classify it into three types, and they are open system, closed system, and isolated system. In open system, both matter and energy can move in and out. For example, in a boiling pot of water, heat escapes, and steam also leaves, which shows that both matter and energy are moving from system. But in closed system, only energy can move in and out, but remember, matter cannot move. To understand it, let's take example. In a closed bottle of hot water, heat can escape, but water stays inside. Now moving to isolated system. In this case, neither energy nor matter can move in or out of the system. A very common example is thermos flask, where heat remains trapped inside and nothing enters or leaves from the system. Now, we can move to another important concept called state functions. Actually, a state function is a property that depends only on the current state of a system, not on how it got there. It means that no matter how we reach a certain condition, the value of the state function remains the same. Some common state functions are temperature, pressure, and volume. To understand it deeply, let's take one example. Imagine you climb a mountain. Your height above sea level is a state function. It doesn't matter whether you took a straight path or a winding one, the final height remains the same. Now, let's talk about two important types of properties, such as extensive and intensive. Remember that thermodynamic properties are divided into two types based on whether they depend on the amount of matter present. And extensive properties are those properties that depend on the amount of substance in the system. For example, a larger object has more mass than a smaller one, and a big container holds more liquid than a small one, which means that mass and volume are extensive properties. Now moving towards intensive properties, these properties do not depend on the amount of substance present. For example, temperature and pressure are intensive properties because a cup of boiling water and a pot of boiling water have the same temperature, and the pressure inside a small and large balloon filled with the same gas can be the same. Now let's discuss fundamental laws of thermodynamics. Actually, thermodynamics is based on four fundamental laws, and they are the Zeroth law, first law, second law, and third law of thermodynamics. These laws explains how energy transfers and transforms in a system. First, let's move towards Zeroth law. But remember that Zeroth law of thermodynamics establishes the concept of thermal equilibrium. Actually, thermal equilibrium means when two objects are in contact, heat flows from the hotter object to the cooler one until both reach the same temperature. Once they have the same temperature, no heat flows between them, and they are in thermal equilibrium. I think now we can move towards statement of Zeroth law. It states that if two systems are in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. Let's understand with simple example. Imagine you have a cup of hot coffee, which is referred as A cold metal spoon, referred as B, and a thermometer denoted as C. If the thermometer first measures the temperature of the coffee and then measures the temperature of the spoon, and both show the same reading, then according to the Zeroth law, the coffee and spoon must also be in thermal equilibrium. Now let's move towards first law of thermodynamics, also known as law of conservation of energy. It states that energy can neither be created nor destroyed, but it can only be transferred or converted from one form to another. This simply means that the total energy of a system remains constant. If a system gains energy, it must have come from somewhere, and if it loses energy, it must have gone somewhere else. Mathematical expression of first law of thermodynamics is delta U is equal to Q minus W. Remember that here, delta U refer to the change in internal energy of the system. Q represents heat, and W stands for work done. Let's take examples to understand it. Imagine heating a gas inside a piston. When heat is added, the gas molecules gain energy and start moving faster, as a result, increasing the internal energy. If the gas expands and pushes the piston outward, it does work on the surroundings. The heat energy added to the gas either increases its internal energy or is used to do work. And as a result, we can say that overall energy is conserved. Now let's move towards second law of thermodynamics. It tells us about the direction of energy transfer and introduces the concept of entropy. Second law states that heat always flows spontaneously from a hotter body to a colder body, and the entropy of an isolated system always increases. This means that natural processes always move toward disorder unless energy is added to maintain its order. Let's understand with example. If you leave an ice cube at room temperature, it melts on its own because heat flows from the warmer surroundings to the colder ice. But the reverse never happens naturally. But a puddle of water does not freeze by itself unless energy is removed. Now it's time to understand third law of thermodynamics. The third law of thermodynamics tells us what happens at absolute zero temperature. And remember that absolute zero refers to 0 Kelvin, or minus 273.15 degrees. Third law states that as the temperature of a system approaches absolute zero, its entropy approaches a minimum value. This means that at absolute zero, all molecular motion stops, and the system reaches perfect order. However, absolute zero is impossible to reach in practice because removing all heat energy completely is not possible. Keep in mind that even in deep space, where temperatures are extremely low, absolute zero has never been achieved. Now let's move towards thermodynamic process. First, let's understand isothermal process. An isothermal process is one where the temperature remains constant, while other properties, such as pressure and volume, change. Since temperature does not change, the internal energy of the system also remains constant. Actually, to maintain a constant temperature, heat energy is either added or removed from the system to balance the work done. If the gas expands, it absorbs heat from the surroundings. If the gas is compressed, it releases heat to the surroundings. Now let's understand adiabatic process. An adiabatic process is one where no heat enters or leaves the system, but temperature and other properties can change. In this process, all energy changes occur due to work done on or by the system. It happens if a system expands, its temperature decreases because it uses internal energy to do work. If a system is compressed, its temperature increases because work is being done on it. Let's make it clear with example of bicycle pump. Air inside a bicycle pump. When you quickly compress air inside a pump, it heats up because no heat has time to escape. Now, moving towards isobaric process. An isobaric process is one where pressure remains constant, but volume and temperature can change. If heat is added, the gas expands, increasing its volume. If heat is removed, the gas contracts, decreasing its volume. Now it's time to understand isochoric process. An isochoric process is one where volume remains constant, but pressure and temperature change. Since the volume does not change, no work is done, and all the energy added or removed goes into changing the temperature and pressure. It usually happens when heat is added. The pressure increases because the molecules move faster in the fixed space. If heat is removed, the pressure decreases because the molecules move slower. For example, if a gas is heated inside a closed cylinder, its volume will not change. Now we will talk about work, heat, and internal energy. In thermodynamics, these terms describe how energy moves within a system and how it interacts with its surroundings. First, let's understand what is internal energy. Actually, internal energy refers to the total energy contained within a system due to the motion and interactions of its molecules. This includes both kinetic energy and potential energy. We must remember that when a system absorbs heat, its internal energy increases. When a system loses heat or does work on its surroundings, its internal energy decreases. Let's take example of hot coffee cooling down. In this case, the coffee's internal energy decreases as heat transfers to the air. Now let's move towards heat. Actually, heat is energy in transit that moves from a hotter body to a cooler body due to a temperature difference. Remember that heat is not a substance, it is simply energy flowing between objects. And always, heat flows from high to low temperature until thermal equilibrium is reached. Now we should understand what are different ways for heat transfer from one object to another object. Keep in mind that heat transfer can happen in 3 ways, and they are conduction, convection, and radiation. First, let's start with conduction. In this case, actually heat transfer through direct contact. For example, a metal spoon in hot soup becomes warm after some time, and it happens due to direct transfer of heat. Now let's understand what is convection. In this case, heat transfer takes place through fluids. To understand it, you can take the example of warm air rising in a room. Now, moving towards radiation, keep in mind that in radiation, heat transfer takes place through electromagnetic waves. We can a very common example to understand it. Sunlight, which is warming our Earth. In this case, the rays of sun are coming towards Earth by radiation phenomenon. Now we should move towards work. In thermodynamics, work is the energy transferred when a force is applied to move a system. Work is done when a system expands or contracts against an external force. Work is positive when the system does work on the surroundings, for example, a gas expanding and pushing a piston. Work is negative when work is done on the system, for example, compressing a gas in a cylinder. The mathematical expression for work in thermodynamics is W is equal to P delta V. Remember that her W is work, P is pressure, and delta V represents the change in volume. Now let's move towards relationship between work, heat, and internal energy. Actually, these three quantities are connected by the first law of thermodynamics, which states that delta U is equal to Q minus W. This equation means that the change in internal energy is equal to the heat added to the system minus the work done by the system. So if heat is added, internal energy increases. If work is done by the system, internal energy decreases. Now let's move towards Gibbs free energy. Remember that Gibbs free energy tells us if a chemical reaction can happen on its own without any outside help or not. It is a very important concept in thermodynamics. The formula for Gibbs free energy change is delta G is equal to delta H minus T delta S. Here, delta G is the change in Gibbs free energy, delta H is the change in enthalpy, T is the temperature in Kelvin, and delta S is the change in entropy. The value of delta G decides if a reaction is spontaneous or not. If delta G is less than 0 or negative, the reaction is spontaneous, meaning it happens naturally. But if delta G is greater than 0 or positive, the reaction is non-spontaneous, meaning it does not happen on its own. And if delta G is equal to 0, the reaction is at equilibrium, meaning it does not move forward or backward. For example, burning wood is a spontaneous reaction because once it starts, it keeps going without any extra energy input. It releases heat and increases entropy, making delta G negative. However, the reverse process turning ash and gases back into wood is non-spontaneous because it requires a lot of energy and does not happen naturally.